Hello student, very good morning to all of you. I think you all are happy, healthy and very fine at home. Do you remember what were we discussing yesterday? I think we were discussing about ipso substituent and what does it mean, or what type of the thing is called as a ipso substituent. Let me tell you, ipso substituent nothing but as a monosubstituted benzene when it is treated with the electrophile, the whatever original substituent present on that benzene itself get replaced by that electrophile. Means whatever substituent present on those carbon atom of the benzene itself get replaced by the electrophile also attack on the same carbon atom and displaces that substituent from the benzene nucleus. So that type of the substituent is known as a ipso substituent with its mechanism and some of the example we have seen that one. So what we are going to discuss today, let us see over here substituent here aromatic nucleophilic substitution reaction, and in short we can call it as a SNAR, or S stand for substitution, N stand for nucleophilic and AR for the aromatic compound. So this is the heading, the aromatic nucleophilic substitution reaction. So here, or we can call it as a substitution nucleophilic aromatic compound. And now here, as we know that when we have started this chapter number 6, the name itself given to this chapter is aromatic, electrophilic and nucleophilic substitution. And as we already studied that the benzene ring, we have already seen that benzene and its derivatives, they readily undergoes, or they easily undergoes electrophilic substitution reaction. Why they readily undergoes, why they readily or why they more easily shows electrophilic substitution reaction? The reason behind it, the benzene itself is a nucleophilic in nature, means number of electron present in the benzene ring is more, and whenever we are adding as a electrophile approaches easily to that benzene nucleus and form the bond. So there is a oppositely charge, means benzene act as a Lewis base and electrophile it is act as a Lewis acid. Oppositely charge they bring together due to the electrostatic force of attraction, and therefore benzene readily undergoes as a electrophilic substitution reaction. And now the remaining thing here is a nucleophilic substitution reaction. Now if you see the nature of that benzene itself is a nucleophilic in nature, and when you are going to add as a nucleophile, so there is a lot of difficulties, because benzene same charge, then nucleophile also has a same charge, there is a strong repulsion. This is the first difficulty, or what we can call it as reason why there is a no nucleophilic substitution reaction occur in a benzene. So that is the first reason, because the pi cloud of the electron, or pi electron cloud repels the nucleophile strongly, and therefore in a simple benzene does not show nucleophilic substitution reaction. Observe the structure carefully, then you come to know that here, as we know, this is a simple benzene, and when this simple benzene we are adding with that nucleophile, as we know that the carbon-carbon double bond, single bond, double bond, they are also as a negatively charged, or electron, as we know that they are the negatively charged in nature. Nucleophile also has an electron rich species, and therefore there will be a strong repulsion between that and therefore what happening here, the second reason, the pi cloud of this benzene is not attacking on that, and suppose as a hydrogen, let it be, and suppose these type of the things are happening, then what is going to happen here? Suppose here is a nucleophile, it is attacking over here, there may be as a hydrogen atom, and now there is a negative charge, and this negative charge cannot be accommodated by that benzene. So this is a nucleophile attack over there, and such type of the intermediate may not be possible in a ordinary condition, and therefore nucleophilic substitution reactions are highly what we can call it as impossible or difficult to introduce the nucleophile to the benzene nucleus in a simple benzene. So it is very difficult, because there are the two reasons just now we have seen. Number one, the pi electron cloud of the benzene nucleus is likely to repel and approaching the nucleophile, and the second reason, the pi electron system of benzene nucleus is much less capable of delocalizing the two extra electron, because this is a two extra electron in the negatively charged intermediate, and therefore intermediate, or this is a, we can call it as a carbanion, and so it is very difficult. And but generally the aromatic compound, they undergoes as a electrophilic substitution reaction. And why they undergoes as a electrophilic substitution reaction, that reason we already know that, but let us see here once again. Here is a this is a benzene. When it is treated with as a electrophile, here electrophiles are easily get attacked over there, and we are going to get as this type of the uranium ion, as we know that here, or we can show like this, or here electrophile, and now here is a positive charge over there, that is a sigma complex, or what we can call it as a this one is a say uranium ion is formed, and that uranium ion now is get what we can call it as a well stabilized due to the resonance. Here we can write as electrophile here, and one here, one double bond here, and this positive charge. So this double bond now shifted from here to here. We can show the resonating structure. Here is a hydrogen atom, here is the electrophile. Now when this double bond shifted from here to here, the positive charge comes on that carbon atom, and this double bond remains as it is over here. And next, what is happening here? This double bond shifted from here to here. We are getting here another structure. The positive charge now comes on this carbon atom. This double bond shifted here, this double bond, and here this hydrogen atom and this electrophile. So in this way, the what we can call it as this, when electrophile is attacked to the benzene ring, whatever sigma complex or the uranium ion, carbocation, that one, carbocation, or what we can call it, this is a uranium ion. That uranium ion are well stabilized due to the resonance structure. These are the different resonating structure or canonical form we can call it as, and these carbocation are well stabilized due to the resonance effect. But in the same benzene ring, when the nucleophile is attacked, what is happening? The extra two, and as we know that this benzene and the nucleophile having the same charge, and therefore number one, they are repelled to each other, they are repelling to each other. This is a first. When benzene itself is a nucleophilic, in a simple benzene we cannot introduce as a nucleophile in the benzene nucleus. They are strongly repelled for each other, and therefore there is no possibility of formation of the bond, no reaction will take place. And second one, the pi cloud, and whatever extra electron in a benzene nucleus, extra electron cannot be accommodated in the benzene sextate, and therefore these two reasons strongly opposes the nucleophilic substitution reaction. That is the reason why this nucleophilic substitution, why is difficult. These two reasons you must remember while talking about the nucleophilic substitution reaction. But what if the substituted substituted benzene is here? As we know that monosubstituted benzene or disubstituted benzene, or what we can call it as a polysubstituted benzene, if the electron withdrawing group present on that benzene, then there is a possibility of introducing as a nucleophile. Means there is a rare cases in a benzene compound they can undergo nucleophilic substitution reaction, but simple benzene do not undergo nucleophilic substitution reaction due to the two reasons just now we have seen, both having as the same charge, therefore they repelling to each other, no reaction will occur. Second one, when the nucleophile is giving as an electron, two electron, that extra electron cannot be accommodated in that benzene nucleus, and therefore the nucleophilic attack on benzene is very difficult. But in some cases, some commonly, suppose as electron withdrawing groups are present in the benzene ring, means substituted benzene ring can undergoes can shows nucleophilic substitution reaction, and therefore we are going to talk about that one is a nucleophilic substitution reaction. Why some of the aromatic compound undergoes as a this one nucleophilic substitution reaction, that we are going to see over here. If the benzene is a substituted as well as whatever the substituent, the nature of that substituent should be, or what we can call it, must be electron withdrawing group if present in the benzene ring, then and then the nucleophilic substitution reaction occurs. What I am saying here, electron withdrawing group present in the benzene ring, then and then reaction is going to occur, and therefore we are going to see here the another point here. We are talking about the nucleophilic substitution reaction. Let us see here the SN2 aromatic reaction, and why it is SN2, that also we are going to see here. S stand for as a substitution. So the aromatic nucleophilic, nucleophilic substitution bimolecular. substitution bimolecular and as we know that SN2 reaction we already learned that SN2 means what? Substitution nucleophilic bimolecular. Same thing you have to remember, and AR stand for the aromatic compound, so you can call as aromatic for sake of convenience. AR stand for aromatic, so aromatic nucleophilic substitution bimolecular, or we can call it as a substitution nucleophilic bimolecular aromatic compound. It doesn't matter, but remember for to talk like this, it looks as a very simple, and that's why we can refer as aromatic nucleophilic substitution bimolecular, or you in short you can remember as a SN2AR, SN2AR, and why it shows as a similarities with that SN2, that also we are going to see and to indicate. And when careful study of that kinetic, you will find that this reaction are the bimolecular reaction. Bimolecular reaction means rate is directly proportional to the concentration of the substrate as well as concentration of the reagent added. Here nucleophile is added, and therefore 2 moles are involved in the reaction, and that's why it is termed as a 2. That is a bimolecular reaction, and it is similar to as a SN2. And in SN2 there is a backside attack, but here is no question about that backside attack, and this is a aromatic nucleophilic substitution reaction over here. And there a nucleophilic substitution reaction, when it is possible, when the strong electron withdrawing groups is present, means strong deactivators are present here. And as we know that nitration reaction, when the benzene nitration reaction takes place, we are getting as a nitrobenzene, and as we know that nitro group is the strongest deactivator, and therefore in such cases what it does, that nitro group is a strong electron withdrawing group, and it withdraw the electron from the benzene nucleus, and therefore that benzene seems to be the electron deficient in nature, and therefore the nucleophile approaches to the benzene nucleus, and there is a reaction takes place. How that takes place, let us see over here. Suppose we have a nitrobenzene, as we know that. Here I am writing as a structure of nitrobenzene. As we know that generally for sake of convenience I am writing as this nitro group is like this. Generally we are writing as a NO2 group. This is a nitrobenzene, right? Nitrobenzene. This is a nitrobenzene, and now this nitrobenzene when it is fused with potassium hydroxide, then hydroxy group get added into this possibility, and therefore OH minus when is fused with that reaction is a slow reaction. Slow reaction, as we know that it is a rate determining reaction. So here what is happening, this negative charge attack over there at with respect to that ortho position, and then this double bond shifted from here to here, and negative charge on that oxygen atom. And because as we know that why this is a possible, because that oxygen atom is more electronegative than the carbon atom or the nitrogen atom, and therefore if you see the mechanistic pathway, then this is a possibility, and therefore we are going to get the product here like this double bond and this double bond, they are remains as it is. Now double bond with that nitrogen and this oxygen they are carrying the negative charge. Here we are putting positive charge, and here again as a OH. Now here there we can loss here as a minus H plus over there, right? And it can pushes, there is a possibility OH, even though in this particular case, or if you compare between these two are the what we can call it as a OH. Now here not H plus, this is a H minus, and as we know that OH minus means hydroxyl group, and H minus we know that this is a hydride. Now there is a loss. Which one is a better leaving group? Here we are comparing between these two only, particularly here. And as we know, while studying as a nucleophilic substitution reaction, where we talk about the which is a good nucleophile or which is good good nucleophile or the leaving group, there we have seen. So here this and this, they are the among these two, if you compare between these two species, particularly here this one is a good nucleophilic, good living group, or what we can call a good nucleophilic than this hydride. But in this particular case, what is happening, there is a, even though it is there, but that hydride get loss here, and we are going to get the compound in a special sorry, not this OH, this hydride get lost over there, and you are going to get the compound here, nitrogen atom, double bond O, and then O minus, positive charge always remains on the nitrogen atom, and this OH is formed, that is orthohydroxy nitrobenzene we are getting, orthohydroxy nitrobenzene, or you can call it as a orthonitrophenol. This is a better way, orthonitrophenol you can call it as orthonitrophenol, or we can call it as a 2-hydroxy nitrobenzene, so depending upon. So this is orthonitrophenol we got over here, and now if you find here the slow means it is a rate determining step. RDS means what? It is a rate determining step, means if you careful study of that rate of reaction, kinetic study directly indicate that rate is directly proportional to the concentration of that nitrobenzene and the concentration of OH minus. Two species are involved, and therefore rate is equal to K2 into concentration of nitrobenzene over here, nitrobenzene into concentration of OH minus, and where we know that K2 means what? That is a second order rate constant, where K2 is equal to second order rate constant, so that is there. So that's why this 2 is there, that is S stand for as a substitution, N for the nucleophilic, 2 for the biomolecular, and AR for the aromatic compound. And why it is a SN2AR? Why? This is the reason why we are writing as a 2 there. So this is similar to as a SN2. Some similarities are there, because if you study the rate of reaction, it is found to be the rate of biomolecular reaction means 2 moles are involved over here, and therefore we are getting as a this type of the compound. So substitution of again other reaction, let us see over here another one. Suppose as a this type of the SN2AR aromatic nucleophilic substitution reaction, this is one of the example we have seen. And now the same reaction, if you see over here, general reaction, substitution of atom other than hydrogens. Suppose as a other than hydrogens, substitution reaction other than hydrogen, then what is going to happen over there? Let us see that also. Suppose we are going to see over here another point, substitution of atom other than hydrogen. Second point we are going to learn here, substitution of atom other than hydrogen. Substitution of atom other than hydrogen. And then how it is taking place? Let us see. Suppose we have this compound, as we know that this one, here is a chlorine atom, and here I am writing as a nitro. The name of this compound, as we know that this is a para-chloro-nitrobenzene. Para-chloro-nitrobenzene, and when it is treated with the nucleophile like as a Y over here, now as we know that here the ipso type of the reaction is going to occur. This nucleophile is going to attack on that chlorine, and you make it as a here nucleophile. Suppose this is going to attack over here, this double bond shifted from here to here, this double bond there, and negative charge on it, and you are going to get the next product here. So here we can write as a chlorine atom that goes backside Cl, and here you can write is a Y product, and now this double bond, it is as it is, and this double bond shifted from here to here. Now the double bond formed between carbon and this nitrogen atom, and O minus charge, here O minus charge, positive charge still remains on the nitrogen atom. When there is a loss of, suppose here is a loss of chlorine atoms over there, how it takes place? The double bond coming over there, and this double bond shifted from here to here, this double bond shifted here to here, and that chlorine atom, that minus chlorine atom get removed easily, and we are going to get the product here, this one. So double bond, and this double bond here, this double bond here, nitrogen double bond O, positive charge as it is, and here we can substitute as a Y over here. So in this way, if you find the rate of reaction, again it is found to be the 2 over there bimolecular, because this reaction is a slow reaction, rate determining reaction, and therefore we can easily determine the rate of the reaction. And now suppose let us see here support for intermediate formation, how this intermediate is formed, that supporting. Here we are going to see one more example, that is a methyl ether over here, methyl ether. Suppose we have this compound over there, support for this. Suppose this is a compound here, methyl ether means anisole type of the OCS3, and I am putting 3 nitro group over there, NO2, and here O2N. 3 nitro means 2, 4 and 6 position, that is a 2, 4, 6 trinitro anisole, that is the name of that compound. When it is treated with, suppose it is treated with ethoxide, what is going to happen? When you treat with this ethoxide, you may get the product over here like this. So here you can write OCH3, and here is a OET is coming over there, and then nitro group may be over there, and or you can instead you can put as a negative charge over there and nitro group NO2, and here O2N, here also as a NO2, and finally OCS3 is lost over there, and you may get as a this type of the compound over there. Here OET, and then NO2, here O not O, NO2, and here also as a O2N. This type, this is a supporting this, and how do you confirm this by using as a NMR spectroscopy. NMR spectroscopy, and this NMR spectroscopy we are going to learn in the next semester, but here just for to confirm the structure of this compound, there are some modern technique we can use over here. One is a NMR spectroscopy, another one is a X-ray diffraction, and by using as a these two technique we can isolate or to characterize such type of the compound by using as a this, and it has been proved possible to isolate and to characterize the intermediate of this of the nucleophilic aromatic substitution reaction by NMR spectroscopy and by X-ray diffraction. NMR we know that nuclear magnetic resonance spectroscopy, and second one is the X-ray diffraction from only one crystal is sufficient to get all the information regarding as a structure of the compound. I think with this we have seen this is SN2 type of the SN2 aromatics type of the reaction. In the next lecture we will see the SN1AR that shows as a similarity with that SN1 aromatic that type, but they are totally different. Only just remember as a kinetically they are what we can call it showing as a some similarity, and therefore we are putting that 2 or 1 over here. So I think with this let us stop today here. Have a nice day. Thank you.